Welcome back to the deep dive. Today, we're embarking on a pretty fascinating journey, really getting into Chapter 6 of Organic Chemistry, the second edition by Clayden, Greeves, and Warren.
That's right.
For those of you maybe following along or, just looking for that quick way to get up to speed, this chapter, it's a real cornerstone. It unveils the reactivity of one of organic chemistry's absolute biggest players.
Absolutely. Our mission today is, well, it's to unpack this really intricate world of nucleophilic addition to the carbonyl group.
Okay.
We'll be hitting the mechanistic reasoning, why things happen. We'll trace reaction pathways, look at functional group changes, touch on stereochemistry, and really see how these sort of fundamental ideas build the foundation for, well, complex organic synthesis later on.
Yeah.
Think of it as your guided tour through this essential chapter.
Yeah, the carbonyl group, that CO double bond.
Yeah.
It's probably the most versatile functional group out there, wouldn't you say? Shows up everywhere.
Oh, definitely. From the simplest stuff to really complex biomolecules.
So we're going to dive into how and why it reacts, look at the orbital interactions, which are always cool, and uncover some maybe surprising real-world applications, things you might not expect. Okay, let's get into this core idea then. Nucleophilic addition. What exactly is happening? And why is that CO group so special?
Right. So at its heart, it's like a little two-step dance. First, you have a nucleophile, something electron-rich, nucleus-loving, attack the carbonyl carbon.
Attacks the carbon, okay.
Then the oxygen atom, which now has extra electrons, usually picks up a proton.
Right.
And the critical bit, you're breaking the weaker carbon-oxygen pi bond, but you're forming a new strong carbon nucleophile sigma bond.
Yep.
It's a fundamental way we build bigger molecules.
Yeah.
Now, why is it so reactive? It really comes down to polarization. Oxygen is way more electronegative than carbon.
Pulls the electrons harder.
Exactly. It's constantly pulling electron density towards itself. So that poor carbonyl carbon ends up with a partial positive charge.
Making it attractive, too.
To anything electron-rich. That partial positive charge is like a big flashing sign saying, attack here, to nucleophiles.
And it gets even deeper than just charges, right? You mentioned orbitals before. It's about the actual shape of the electron clouds.
Precisely. Yeah, to really get the why, you got to look at the molecular orbitals. Specifically, the nucleophile's highest occupied molecular orbital, the HOMO. That's where its available electrons are.
Okay.
And that HOMO interacts with the carbonyl group's lowest unoccupied molecular orbital, the LUMO. Now, this LUMO, it's the pi star, the antibonding orbital. And it's not spread out evenly. It's heavily skewed towards the carbon atom. Think of it like an empty landing strip.
Yeah.
Mostly just on the carbon.
Ah, okay. So
Yeah.
the electrons aim for that spot.
Exactly. Electrons flow from the nucleophile's HOMO right into that pi star LUMO on the carbon. When that happens, the pi bond between carbon and oxygen breaks.
Yeah.
And those electrons just swing up onto the oxygen.
And the shape changes too, right? You mentioned that.
Crucial point. The carbon atom starts out flat, trigonal planar, and we call it sp2 hybridized.
Right.
But as soon as it accepts those electrons and forms the new bond, boom, it becomes tetrahedral, sp3 hybridized. It literally pops out of the plane.
It's a fantastic visual. Okay, let's ground this. A real reaction example. The chapter starts with cyanohydrin formation.
Yep, a classic. Cyanide ion, CN, uses its electron-rich sp orbital to attack aldehydes or ketones.
And the product is?
You get an alcohol with a nitrile group attached right next to it. That's your cyanohydrin. Often you need a bit of acid around to protonate the oxygen anion that forms initially.
Now, these are just like textbook examples, are they? Where do cyanohydrins actually show up?
Oh, no, they're really important. They're key intermediates in synthesis. For instance, they're used to make some medicinal compounds, like certain 5-HT3 agonists.
What do those do?
They help reduce severe nausea, like for chemotherapy patients. Cyanohydrins are also building blocks for some insecticides, like cypermethrin. You might even have that at home.
Wow, okay.
And what's really interesting, chemically speaking, is that this reaction is reversible. Cyanide can actually leave again.
It can just pop back off.
Yeah, it's a reasonably good leaving group. And this reversibility, it have major real-world implications. Think about cassava.
The root vegetable.
Exactly. A staple food in parts of Africa. It naturally contains a compound, a glucoside, which can break down to acetone cyanohydrin.
Okay.
If it's not prepared properly, enzymes can break that down further, releasing highly toxic hydrogen cyanide gas, HCN.
That sounds dangerous.
It is. That's why proper preparation, like long fermentation, is absolutely crucial to remove the HCN and make it safe to eat. It also shows how steric hindrance bulkiness around the carbonyl affects the equilibrium. Aldehydes favor the product more than ketones do.
Okay, so sterics influence the equilibrium. You also mentioned the shape change. Does the direction the nucleophile comes from matter? Is there like a preferred angle?
Absolutely. It's very specific. Nucleophiles don't just bump into the carbon randomly. They approach at an angle of about 107 degrees relative to the CO bond axis.
107 degrees. There's a name for that.
Yep. The Brigidinous trajectory. It's like the sweet spot maximizes overlap between the attacking HOMO and the receiving LUMO while minimizing repulsion from other electrons.
So anything blocking that path
will slow the reaction right down.
Yeah.
That's steric hindrance in action, blocking the ideal approach.
Okay, that trajectory idea is really neat. So we've attacked with cyanide. What if we want to reduce the carbonyl, add hydrogen, not carbon? How do we do that? Just throw in high GH.
Ah, good question. You'd think 8 would be the obvious choice, but it's generally too basic, too reactive on its own. Instead, we use what we call hydride donors. A really common one is sodium borohydride, NaBH4.
Sodium borohydride. Okay.
It's a tetrahedral anion, BH4 minus. But the nucleophilic electrons don't come from a lone pair on boron. They actually come from one of the BH bonds itself.
So the whole BH bond acts as the source of the hydride.
Essentially, yes. It delivers H minus to the carbonyl carbon.
Yeah.
And the result is you aldehydes and ketones down to alcohols. A really clean reaction. And a big advantage of NaBH4 over, say, stronger things like lithium aluminum hydride.
Which is another reducing agent.
Right. Much stronger, much more reactive. NaBH4 is milder. You can actually use it in water or alcohol as the solvent, which makes life much easier in the lab.
Versatile. But does it just reduce any carbonyl it sees? Or is it picky?
That's a really important point, selectivity. No, it's definitely picky. It's slower with ketones than aldehydes, again, because of sterics.
More crowded around the ketone carbon.
Exactly. But crucially, NaBH4 is highly selective for aldehydes and ketones. It generally won't touch less reactive carbonyls like esters or amides.
Oh, interesting.
Nor will it usually react with things like nitro groups or alkyl halides. This is super useful if you have a molecule with multiple functional groups. You can zap the aldehyde or ketone without messing up an ester elsewhere.
Like a precision tool.
Precisely. Chemoselectivity, we call it.
Okay, so we've added H with NaBH4. But what if we do want to build a bigger carbon framework? Add a carbon group, not just hydrogen. What are the go-to reagents then?
Now we bring out the big guns. Organometallic reagents. Things like organolithiums, RLI, and especially Grignard reagents, RMGX.
Grignards, heard of those.
Yep. In these, you have a carbon atom bonded directly to a metal, like lithium or magnesium. That C metal bond is heavily polarized the other way.
Making the carbon negative.
Effectively, yes. Very electron-rich. A powerful nucleophile and also a strong base. Perfect for making new carbon bonds by attacking carbonyls.
Oh.
And when they react with aldehydes or ketones, you also end up forming alcohols after the workup. But the type depends on what you start with. An aldehyde gives you a secondary alcohol.
And a ketone.
Gives you a tertiary alcohol, so it's a great way to build complexity.
Now, you said they're powerful nucleophiles and strong bases. I bet the reaction conditions are pretty strict.
Oh, absolutely critical. Because they're so reactive, they react violently with proton sources like water.
Yeah.
Even with oxygen in the air.
Yikes.
So you have to run these reactions cold, often very cold, like minus 78 Celsius, dry ice temperature.
Minus 78.
Yep. And interproduct solvents without acidic protons like ether or THF, and all under an inert gas like nitrogen or argon to keep air and moisture out.
And then you add water later.
Exactly. Only after the organometallic is fully reacted do you carefully add water or dilute acid to protonate the oxygen. That's the workup step. It's all about controlling that reactivity.
Okay, so we've covered charged nucleophiles like cyanide, hydride donors, and these super reactive organometallics. Do nucleophiles always need to be charged or highly polarized? What about just like water or an alcohol?
Good point. No, they don't. Neutral nucleophiles like water and alcohols can definitely add to carbonyls too. Take formaldehyde, the simplest aldehyde, dissolve it in water.
Yeah.
And if you look at its 13C NMR spectrum, you basically see no carbonyl carbon signal. Instead, you see a new signal for a tetrahedral carbon bonded to 2 oxygens.
So the water added across the double bond.
Completely. It fully hydrates to form a 1-1 diol, or a gem diol. And this hydration, just like the cyanohydrin formation, it's in equilibrium. And the same factors influence how much hydrate you get. Sterics matter aldehydes hydrate more than ketones.
Less crowded.
Right. And electronic effects, too, if you have electron withdrawing groups nearby, like halogens.
Like chlorine.
Exactly. Think of chloral, which has 3 chlorines. Those pull electron density away, make the carbonyl carbon even more positive, more attractive. Chloral hydrate is basically the only form you find in water.
And you mentioned ring strain earlier. Does that play a role here too?
It sure does.
Ooh.
Cyclopropanones, those tiny 3-membered rings with a carbonyl, super strain.
Yeah, it must be.
Adding water helps relieve that strain because the carbon goes from that constrained sp2 state to a much happier tetrahedral sp3 state.
Yeah.
So they hydrate quite readily. And it's a very similar story with alcohols adding to carbonyls. They form hemiacetals. Again, similar mechanism to water, also reversible.
Hemiacetals. Okay.
But these hemiacetals become much more stable, much more favored if they form a ring, an intramolecular reaction.
Meaning the alcohol and carbonyl are in the same molecule.
Exactly. The alcohol part of the molecule loops around and attacks the carbonyl part. This forms a cyclic hemiacetal, often called a lactol, and this is hugely important in biochemistry.
How so?
Well, think about sugars like glucose or ribose. In solution, they mostly exist as these stable cyclic hemiacetals, not as the open-chain aldehyde forms you often see drawn initially. It's the dominant form.
Ah, okay. So that ring structure is key for sugars. Now, with all these reactions, especially the reversible ones like hydration and hemiacetal formation, can we nudge them along, speed them up, use catalysts?
Absolutely. Both acid and base can catalyze many of these additions.
How do they work differently?
Okay, so acid catalysis works by protonating the carbonyl oxygen first. That makes the carbonyl carbon even more electron deficient, even more electrophilic, so the nucleophile attacks faster.
Makes the target bigger, effectively?
Sort of, yeah.
Mm.
More attractive. Base catalysis works the other way around. It makes the nucleophile better. For example, it can pull a proton off water or an alcohol to make hydroxide or an alkoxide.
Which are much stronger nucleophiles.
Exactly. So they attack faster. And in both cases, acid or base, the catalyst gets regenerated at the end, so you only need a small amount.
Clever. Are there any sort of practical applications of these reversible additions, maybe for purification?
Yes, definitely. Sodium bisulfite addition is a great example. Bisulfite anion, HSO3, adds to aldehydes and some unhindered ketones.
Okay.
And the resulting addition products are often crystalline solids and usually water-soluble, even if the original aldehyde decatone wasn't.
Ah, so you can crystallize it out.
Precisely. Because the reaction is reversible, you can form the solid bisulfite adduct, filter it off pure, and then treat it with acid or base to regenerate the original pure carbonyl compound. It's a neat purification trick. They can also be useful intermediates. You can actually make cyanohydrins via the bisulfite adduct sometimes. It's a way to generate the cyanide in situ and provide the proton source without handling HCN gas directly. Safer.
That is smart.
And that solubility difference is also used in medicine. Think about dapsone. It's an anti-leprosy drug, very effective, but very insoluble in water.
Making it hard to administer.
Exactly, especially in remote areas without sophisticated facilities. But you can convert it into a water-soluble bisulfite adduct. This allows it to be formulated as an aqueous solution, making treatment much more accessible. Simple chemistry, huge impact.
Wow, what an incredible tour of the carbonyl group and just this one type of nucleophilic addition from the orbital interactions, the angles of attack.
The Burgidoon in its trajectory.
Right. All the way to making medicines for chemotherapy or leprosy, and even understanding why you have to prepare cassava carefully. It's all connected back to this CO group, just like Chapter 6 lays out.
It really is. And understanding that mechanistic reasoning, why an ABH4 is selective, why Grignards need special conditions, how catalysts work, it lets us predict what will happen, control reactions, build things intentionally, forming new bonds, new functional groups. It's a beautiful, logical system.
It really makes you stop and think, doesn't it? How many compounds we rely on or even need to be careful of trace their properties right back to this elegant dance of electrons around a carbonyl. So much complex chemistry just sort of happening.
It's a fascinating thought to carry away. The power of understanding these fundamentals is immense.
Well, that's all the time we have for this deep dive. Thank you, as always, for being part of the Last Minute Lecture family. We look forward to exploring more chemistry with you next time.